This is a short video on page 3 of your notes, which is on exceptions to the octet rule. So octet rule states that elements want 8 valence electrons, okay, which hopefully by now you know. All elements want to get 8 valence electrons. Obviously, elements on the right side of the stair step, the nonmetals, are trying to gain electrons. So family 17 wants to gain 1 electron. Family 16 wants to gain 2 electrons to get to 8 valence. The elements left of the stair step, or even family 13 to the left, want to lose electrons. So 3 exceptions would be this. First one, which you guys already know. I'm sorry, first one you do not know. Some elements have an odd number of valence electrons. This is the most uncommon one by far, the least important one. So these two have an odd number of valence electrons. So nitrogen's got 5, oxygen's got 6, but there's 2 oxygens. So you got 12 plus 5, there's 17 valence electrons here. So if I draw this, I go O with an O and give everything. That's got 8, that's got 8, that's got 8. If I do that, that is 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that is 3 too many. So whenever we've used too many, there's more sharing. So make a double bond, erase, erase. That is still 18. Okay. The element that normally has an odd number is the one with an odd number of valence electrons. Okay. This is not a stable compound. It tends to bond to something else. Actually, what it tends to do is become the nitrite ion with a -1 charge. It tends to pick up another electron from somewhere else, or it combines with another atom, such as potassium, which has a valence electron for it. Okay. Another example of that is NO. Again, this is probably my least important out of these things, but 5 valence plus 6 is 11 valence. So if I try to draw this, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's got 8, that's got 8, 2, 4, 6, 8, 10, 12. That's 14 electrons. Okay, so if I go there, erase, 2, 4, 6, 8, 10, 12, that's still too many. Okay. The element that was odd to start with probably has an odd number. Not common. Okay, not common. So it's probably the exception I'm least concerned about. Next one is one that happens often. Actually, all ionic compounds do the next one. So next one's a little more important. Last one's most important probably. Some elements have less than 8 electrons around them. This is going to be the central atom typically, or hydrogen. So this is true for every element from the boron family, family 13, from the boron family left. All the elements that have 3 valence electrons or less will always have less than 8 electrons around them, because they're giving away their electrons. They're not trying to get to 8 valence. They're giving away their valence electrons to empty out their outer level. So a couple examples here. So I've got BH3. Again, boron's got only 3 valence. It tends to lose its 3 valence electrons. Even though it's right at the stair step, it does not do that. So 3 valence electrons. Each hydrogen's got 3, or got 1, so that's 3 electrons, or 6 total. But a boron, 2, 4, 6. Okay, there's no unshared pairs on it. Boron only has 6 around it. Again, it's family 13 to the left. The elements with 3 valence electrons to the left. This would be a trigonal planar shape, remember, because there's no unshared pairs on here, so it'd be evenly. These electrons are evenly distributed around there. Magnesium chloride. This is an ionic compound. Again, magnesium is a metal. It's got 2 valence electrons. It's just getting rid of those. So magnesium will not have 8 around it. So again, every element from family 13 to the left will have less than 8 electrons around it. Last exception, this is the one I spend the most time on. This is called an expanded octet. It's called an expanded octet, which means you have more than 8 electrons around the central atom. More than 8 around the central atom. It's pretty easy to tell this. You know, if you have a compound like CH4, you know there's a carbon with 4 things around it. That is not going to be an expanded octet. But if you see a number bigger than 4 back here, a 5 or a 6, then you can tell it's probably going to be an expanded octet. Or if you see a noble gas, particularly xenon. If xenon forms a compound, it has an expanded octet. It's going to have more than 8 electrons around it. Okay, so you got, if you see a number bigger than 4, or if you see a noble gas like xenon, which is not very common either. So if I count the valence electrons here, phosphorus has got 5 valence, chlorine's got 7 valence, but there's 5 of them. So 7 times 5 is 35, plus 5, you got 40 valence electrons to use. Remember, we need to use all 40 of those electrons and give everything 8. So if we put a phosphorus in here, we think about normally phosphorus would have 1, 2, 3, 4, 5 valence. It usually wants to gain 3 electrons to get to 8. In this case, chlorine is going to take each of its valence electrons. So phosphorus is essentially giving away all of its valence electrons. So if I go a chlorine, 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 and chlorine. So I put 5 chlorines around it. So that is 2, 4, 6, 8, 10 electrons I've used out of the 40. That means phosphorus has more than 8 around it. Usually the elements that do this will be from the families 15, 16, or 17. Okay, usually family 15, 16, or 17 will have an expanded octet if possible. Again, each chlorine needs to have 8 around it, so you've got 2 there. Put 6 around each one. If we count all of our electrons, there's 8 on each spot. 2, 4, 6, 8. 2, 4, 6, 8. Remember the bond counts as 2. So we've used 40 electrons. Right? This one would be very similar. You're going to have a sulfur in the middle. I'm going to draw this one quickly. You're going to have a sulfur in the middle. You're going to have a fluorine, a fluorine, a fluorine, fluorine, fluorine. So you're going to have 6 fluorines around sulfur. That's an expanded octet around sulfur. Again, what's really happening here is sulfur is giving away each of its valence electrons, all 6 of them, and forming 6 bonds. Each fluorine would have electrons around it. Now, in terms of shapes, so before we had just done linear, trigonal planar, trigonal pyramidal, bent, and tetrahedral. So here are the shapes, again, in your packet of notes. These are the shapes of the expanded octet. So this column here, this is saying that there's 5 pairs of electrons around the central element. So it's kind of like when we had that phosphorus with 5 bonds coming off. This means there's 6 pairs of electrons around the central element. So these are expanded octets. There's more than 4 pairs of electrons around the central element. There's more than 8. So this would be 5 pairs or 10 electrons around the central element, 6 pairs or 12 electrons around the central element. So this is telling you the number of unshared pairs or lone pairs. So in this molecule, it's got 1, 2, 3, 4, 5 bonds. In other words, 5 shared pairs. It's called trigonal bipyramidal. This one, seesaw, has 1, 2, 3, 4 shared pairs, 1 unshared pair. So it's telling you 1 unshared pair, 4 shared pairs. So you can kind of look and see how that goes. 1, 2, 3 shared pairs, 2 unshared pairs. So you can kind of look from there. Down here, this has 6. This one's got 6 bonds coming off of it. It's called octahedral because it would be, if I could draw shapes, if I could draw this as a figure, 1, 2, 3, there'd be a 4-sided figure on top and a 4-sided figure on bottom. That's why it's called octahedral. It'd be an 8-sided figure altogether.